This is solar cell. So using sunlight, the solar cells are working and the electric current is generated. Let's see how it works. You got your positive and negative electrodes here, and this is a solar cell. A solar cell is basically a PN junction which generates EMF when solar radiation falls on the PN junction. So here is the metal contact and there is an anti-reflecting coating. You are able to see the energy diagram and the current is generated. It works on the same principle of photoelectric effect and photovoltaic effect as the photodiode, except that no external bias is applied and the junction area is kept much larger for solar radiation to be incident, because we are interested in more power, obviously. A P-type silicon wafer, a PSI wafer, is about 300 microampere is taken over with a thin layer of N silicon is grown on one side by diffusion process. A P silicon wafer of about 300 micrometer is taken over with which a thin layer of N silicon is grown on one side by diffusion process. You are able to see the N silicon wafer on and a P silicon wafer of about 300 micrometer. The other side of P silicon is coated with a metal, that's a back contact. On the top of N silicon layer, metal finger electrode is deposited. A metallized finger electrode is deposited. This acts as a front contact. The metallic grid occupies only a very small fraction of the cell area. The generation of EMF by a solar cell when lights fall on, it is due to the following three basic processes. The first one is generation, the second one is separation, and the third one is collection. So here is a solar cell and you are able to see it is connected, both the ends of the top and bottom is connected to the electricity and you are able to see the bulb is glowing. The electrons reaching the N side are collected by the front contact and holes reaching the P side are collected by the back contact. Thus P sides become the positive and N side becomes negative, giving rise to photovoltage. Here is a typical example. You got a P and N and you are able to see the light radiations are passing and this is the depletion layer and the entire circuit is connected. Let's discuss more on the current versus voltage characteristics of a solar cell. So we'll talk about the EH pass due to light with the H nu. H nu is nothing but your current, your photon voltage. It's greater than Eg to close to the junction. The separation of electrons and holes due to the electric field is done by the concept of depletion layer. You can see the depletion layer, a line. The current versus the voltage characteristics of a solar cell is drawn in the fourth quadrant of the coordinate axis. This is because a solar cell does not draw current but supplies the same to the load. Semiconductors with a band gap close to 1.5 electron volt are the real ideal materials for solar cell fabrications. The solar cells are made with the semiconductors like silicon and it got a Eg value of 1.1 electron volt, and gallium arsenide which is having 1.43 electron volt as Eg value. It's nothing but your energy gap. And cadmium telluride, it's of almost 1.45 electron volt. And finally copper, indium gallium selenide, which is having a electron gap or energy gap which is almost 1.04 electron volt. The important criteria for the selection of the material for solar fabrications are the band gap. It's approx of 1.0 to 1.8 electron volt. The high optical absorption is almost 104 per meter, and it should have a high electrical conductivity. So availability of the raw materials, and finally the cost. These are the things which is needed for a solar cell fabrication. So the solar cells are used to power electronic devices in case of satellites and space vehicles, and also as a power supply to some calculators. You are able to see the solar panels from sunlight. The solar panels are generating electricity and it is used for the electronic devices. The production of low cost photovoltaic cell for large scale solar energy is a topic of research now.